How does high dimensionality affect machine learning? Imagine trying to find your way through a maze that keeps expanding as you walk. That's what high dimensionality does to machine learning data. When datasets have many features or variables, it creates a lot of challenges. This is often called the curse of dimensionality. As the number of features increases, the space where data lives gets bigger and bigger. The data points become spread out and sparse, making it tough for algorithms to spot patterns. Think of it like trying to find a friend in a huge crowd where everyone looks alike. It's hard to tell who is who. One big problem is data sparsity. When there are too many features, most of the space is empty. This makes clustering and classification difficult because similar data points are rare. Distance measures, which help algorithms like k-nearest neighbors decide how close points are, lose their meaning. In high dimensions, the distance between any two points becomes almost the same, so the algorithm struggles to tell them apart. Another issue is the increased computational load. More features mean more calculations. Training models takes longer and needs more processing power. For example, working with thousands of image pixels or text features can slow things down significantly. Plus, models tend to overfit. They start to learn noise or random fluctuations in the data instead of real patterns. This means they won't perform well on new and seen data. Visualizing high-dimensional data is also tricky. Humans find it hard to interpret data with many features. It's like trying to see a complex sculpture in a tiny picture. To fix these problems, we use techniques called dimensionality reduction. These methods simplify the data by transforming it into fewer features while keeping the important information. Principal component analysis is a popular method that finds new features, called principal components, which capture the most variation in the data. Other techniques like t-distributed stochastic neighbor embedding and uniform manifold approximation and projection help visualize complex data by preserving local and global structures. Feature selection is also useful. It picks out only the most relevant features and discards the rest. This makes models faster, less prone to overfitting, and easier to interpret. In real-world artificial intelligence applications, high-dimensional data is everywhere. For example, images have thousands of pixels, and text data can have hundreds or thousands of features. Deep learning models like neural networks are designed to handle this complexity. They learn hierarchical patterns, which helps them process high-dimensional inputs without the same issues traditional algorithms face. Managing high dimensionality responsibly is important. It helps prevent models from overfitting or producing biased results. Dimensionality reduction makes AI systems more efficient and easier to understand, especially when working with complex data like images, text, or multimedia. So, high dimensionality can make machine learning more complicated by spreading data thin and increasing processing time. It also makes distance-based methods less reliable. Using techniques to reduce the number of features helps keep models accurate, fast, and easier to interpret. That's why understanding and applying dimensionality reduction is such a key part of working with complex data in machine learning.